So we're going to now take a look at solving a system of linear equations by graphing. The directions say solve the system by graphing. Now, the system of equations is basically two or more equations, and the solution is basically the value of the variables that make both equations or all of the equations true. Okay, so in this situation here, I'm going to have an xy if I have a solution. Maybe I'll have an infinite number of solutions, but this would be a solution is a particular xy point that makes this true and that true. Okay, that's what a solution of a system means. All right, let's take a look at finding this by graphing. There are three ways to find a solution to a system, and we're going to go through all three of them. This first video is going to deal with the graphing. So let's take a look at this first red one. I'm going to begin by finding the y-intercept, which is that -3 at the end there. And then I'm going to take the slope of -3/1 and go ahead and plot that down 3/1. And there are some guide points. And go the other direction. And, of course, here's my line. Now, when I'm trying to graph something, when I'm trying to graph a system, I need to be very, very careful and accurate because I'm looking for a particular point on the coordinate grid. And so let's see here. We have that one on there, and then this one, this green line doesn't have a y-intercept, so if I wanted to, I could put a +0, and that would mean that the y-intercept, that doesn't change the problem, right? So I'm okay to add the 0, and then I'm going to go down 3/2. Down 3/2. Down 3/2, and I'm going to go the other direction, and look at there, hits right on that. Okay, 3/2. Okay, so let's make sure that that looks like a line when I connect it. Alright, so here's the system graphed. Now let's identify the solution. The solution is found where we have a coordinate point at -2 up 3. So this is the solution. Now here's how I write that. I write it as a set. It's a solution set, and that's why I do that. I just put that point, that coordinate point, in a solution set like that. -2, 3. Now let's just say I'm 99%, maybe 95% sure that that's correct. Here's what I can do. Take this equation, rewrite it with this value and this value in the respective places. So let's see, 3 is equal to, that's +6 minus 3, 3 is equal to 3, and it checks. Okay, let's write this one down here, and let's check this one. They both have to, it has to work in both of them, excuse me. So we have y equals -3/2 x. So now I'm going to put in 3 equals -3/2 times the -2. So 3 equals, this is 2/1, the 2's cancel, I get -1 times 3, -3 is 3, and that also works. So if you are not sure if your answer is correct, if you're not sure your drawing has been accurate enough, then you can actually check it by substituting back in. Okay, let's take a look at a couple of others. Alright, we're going to take a look at this one. 4x minus y is 3, and we'll go with this one, 8x, oops, excuse me, minus 2y is equal to 6. Alright, now as you can see, these are not in the same form as the other two lines. The other two lines were in the slope-intercept form. Well, these two lines are not in the slope-intercept form. These two lines are in the standard form of an equation of a line. Ax plus by is equal to c. And when I find lines in this form, I'm probably going to graph them a different way. So I'm probably going to use x and y intercepts. So let me put this on here, x-intercept, y-intercept for this blue one. And these are going to give me 2 points on the x and the y-axis, right, a point on each axis so that I can just connect the dots. So I won't use slope in this method of graphing. So to get the x-intercept, I make the y 0. So if you make the y 0 on that, you see that you have 4x is equal to 3. You have x is equal to 3/4. Okay, so I'm going to go to 3/4 on my x. Okay, roughly estimate that. My y-intercept is when the x is 0, negative y is equal to 3. Y is equal to negative 3, and so I'm going to go ahead and put that like that. Okay, now that's my line. Okay, now I'm going to do the green one in the same way. My x-intercept, my y-intercept. X-intercept is when you make the y a 0, so that would cause this to be this. X is equal to 6/8. Well, if I reduce that, that's equal to, divide by 2, I get 3/4. Oh, look at there. 3/4. The y-intercept is when I make x 0, negative 2y is equal to 6. Just put in a 0 for x, right, and it makes it go away. Y is equal to negative 3. And I see that this line is the same as the other line. So if solution means the places where they touch, or the places that x and y are actually values that work for both of them, then there would be an infinite number of xy coordinate points that would make this work. So here's how we write that. Since the solution is an infinite number, then we write this. We give our solution set like this, and we say x and y are such that, there's the such that, and then I'm just going to write one of the equations. I can write either one, such that there's that relationship between the two. That's what this means. It means x and y such that, so there's the such that, I have this relationship between the x and the y, right, at every turn. So there's the solution for that. Okay, and this is called infinitely many. We'll talk about that the last part of the video a little bit more. And let's look at one last one for this video, and that's this. One-third x plus 2. And my other equation is going to be, let's go with blue, 3y minus x is equal to 15. Okay, let's take the red one. I'm going to go ahead and, because it's in y equals mx plus b form, the slope-intercept, I'm going to go ahead and start with the y-intercept, and I'm going to go up 1/3. So you can see that if the y is already alone, it's a little bit faster to graph. You know, I can always get the y alone if it's not, but I kind of like to keep my skills practiced in different methods. So there's that one, and then I'm going to go ahead and graph the blue one, and just for kicks, I'm going to go ahead and get the y alone. There's just another way I could go about this. Get the y alone, so divide by 3 on everything, and I get 1/3 of x, right, when I divide by 3, and that's that. So let's see what we have here. We have a y-intercept of 5, and I'm going to go up 1/3, and look what you can see what's happening. These are, of course, they're parallel lines. If the slope is the same and there's a y-intercept that's different, two things, slope is the same, y-intercept is different, then we have parallel lines. If the slope's the same and the y-intercept's the same, we don't have parallel. We have the same line. Okay, so there they are. Now, if solution to a system means the places where they touch, or the places that they share values of x and y that they share that would make the equation true, there aren't any. They don't share any points, and so we actually call this type of solution no solution. Okay, you could actually do this like that, null set, and we don't put that little null in a set. We just say that means null set. There's nothing for the set of solutions. Okay, let's take a look at one more quick thing. Excuse me. And that's this. Just to give you a schematic for the ways that we can have solutions to systems, we have this situation. We have either they're consistent, and I've just given you examples of these, or inconsistent. consistent or inconsistent. Consistent means, and here's what I just like to remember, that they're touching. They touch. And these, they don't touch. Inconsistent means they don't touch. Right? So, after we discover that they touch, there's two ways that we can break it down. Okay? And that would be whether they were independent or dependent. Okay? Now, independent means they touch exactly once. And dependent means they touch an infinite number. So you can go back, go back and see the picture of that. Infinitely many times. Okay, so there's the kind of the schematic if you want to identify the category to which these belong. Okie doke. Thanks for watching.